So deep learning is really exciting, and especially for deep convolutional neural networks, things have been layering up. So we have this cake in Singapore called the Kueh Lapis, which is just a 1,000-layer cake, and that's exactly a good synopsis of what's going on in CNNs. So the idea is that we have layers upon layers of convolutions, pooling, pairing of layers being replicated several times over to get incredibly good performance. So looking at this infographic, we have 2010, 2011, 2012, all the way to 2016 here. And you can see at the beginning, we basically have traditional machine learning methods working very well. But starting with the inception of AlexNet in 2012, we have convolutional neural networks taking the lead, where we're using multiple layers to accumulate results and do the feature engineering automatically through the neural network. And so we'll be studying AlexNet as well as VGG and the ResNet to get an idea of how these different architectures are assembling really great results in object recognition. So I should say that this particular bar chart is talking about the ImageNet Large-Scale Visual Recognition Challenge. That's what this acronym stands for. And so you can see that what's happening is that the number of layers that are being used in each of these algorithms is steadily increasing. So we have at this point in time in 2016 or so over 200 layers in the neural networks that are being engineered to get good performance. And let's see why that's the case. So we've already talked a little bit about how CNNs alternate between using a convolution layer. Of course, that convolution has to be paired with an activation function to get the nonlinearity. And then using a pooling layer usually after that, as you can see here. So we have a convolution with an activation, then a pooling, then a convolution, then a pooling, then a convolution, to be able to engineer more complex features as we go up, but also at a higher resolution. That means its visual field or receptive field is bigger. And oftentimes we'll use a fully connected layer at the end of the network so that we can combine all of the visual features that have been engineered at the complex level and pull them together to get the classification output. Let's take a look first at AlexNet. So this is the ImageNet competition, which has 1,000 different classes of objects that you need to recognize within an image. And this was the first big win for deep convolutional neural networks. You can see here what it was doing is going from an input that's about 227 square RGB inputs, so 3 channels. And basically we're doing these types of operations where we're doing a convolution with a max pool. Sometimes there's a normalization layer. And then finally we do a fully connected layer at the end. And at the beginning you can see there's going to be a lot of memory used for all of the input dimensions. So we have 227 by 227 images, but by the end, when we come to the last few layers, we only have an image that's about 13 by 13 in size, but we have many different features that we've engineered, 256 different features that have been created for the upper layers. So there's more memory involved, but many more parameters at the bottom layer. And you can see this right here because the last few connected layers, these are all 4,000 units being connected to the next 4,000 units, so that's 4,000 squared number of parameters at this level. So could we do better? So the second deep network that we're going to study is the VGG net. This was created by the Visual Geometry Group at Oxford, and it was the winner in 2 years after AlexNet debuted at the Large-Scale Image Recognition Challenge. The key idea behind VGGNet is that certain types of convolutions, for example, the ones down here, the 5 by 5 and 11 by 11, are horribly expensive. Let's take a look at this topology here, a stack of 2 3 by 3 convolutions and a 1-layer 5 by 5 convolution. So the 5 by 5 convolution will have 25 parameters because it's 5 by 5, plus 1 bias weight, so I have 26 parameters in total. Okay, now when we take a stack of 2, remember that this convolution here, as well as this one over here, they're actually the same filter. So we actually have only 9 plus 1 parameters for this bottom layer. Okay, and for this upper layer here, again, another filter that's being learned, and that also has 9 plus 1 or 10 parameters. So here we're getting 20 parameters, here we're going to get 26, but yet, because we're doing two nonlinearities, we are gaining expressiveness. So the key here is that we have the same amount of pixels being seen by the filters, but we have a larger amount of expressiveness that we can encode. So what VGGNet does is basically discards these two convolutions because they're expensive and dispense with that, and instead use the extra parameters to create more convolution plus pooling pairing levels, and that leads to better performance. So in 2015, we had the appearance of ResNet, or residual network, that was pioneered by Microsoft. And you can see it starts to get pretty insane from here. We had VGG on the last slide that had 16 or 19 layers, depending on the variant. And Microsoft went ahead and did a 34-layer system. And then eventually the one that they submitted for the ImageNet competition had 152 layers. And this again eked out even better performance, lowering the error rate by almost 50%, which is really, really good, doing as good as human level performance actually at certain points. And to do this, they built the idea of a residual module. Okay, a module that explicitly tries to learn additional nuances that are not captured by previous layers. Their insight was to take the gradient that comes from the previous layer and feed it in to a subsequent layer farther down. So you can see all of these blocks over here. They're just modules stacked on top of each other, and each of them is required by the topology to learn something new. So the idea is that each of these blocks has to learn something that the previous layer didn't capture, and if for whatever reason it's not able to tune anything useful from this convolution, it will just learn the identity X. The skip connections will allow the error to propagate to the next level. So in some sense, using a residual block doesn't hurt, because we can add as many layers in the network, and we are only going to get better performance because we're only learning from the residual errors that are left over that the previous layers haven't been able to capture.